We spoke of the category of natural numbers, where objects are natural numbers. And morphisms are functions between sets that have the size of that number. So if I've got two natural numbers n and m, a morphism from n to m is a function from an n element set to an m element set. And we do want to consider the case when n is 0 as well. When n is 0, this set of numbers from 1 to n is regarded as the empty set, because there is no way to go from 1 to 0 by increasing the numbers, and the three dots here refer to increase of numbers. Now, composition of morphisms is the usual composition of functions. So if I have a diagram with f and g, then the composite of g and f will evaluate at x, will give the value g of f of x. So this is the category in which we were working at the end of the previous lecture. And what we discussed in the previous lecture was a construction that captures addition of numbers. So we drew a certain diagram. We had, maybe the letters will be different from what we had last time. We had n, and then we had these functions, kind of insertion functions. The first one, called iota1, would map x to itself. And the second one, iota2, would map y to n plus y. So if I think of this geometrically, this set n, think of it as a sequence of dots, and the same for the set m. And to distinguish the two sets, we can insert some colors there. Now, in the sum object, n plus m, we're going to have as many sorry, I'm just figuring out my copy and paste here. As many dots as we had in the first one plus the second one. So our picture for the sum will look like this. Without the without this border, but then the functions are just insertions of the orange part into the orange part and the green part into the green part. So we spoke of the fact that this diagram consisting of n plus m in these special functions between these has the property that if I have any other object k and any two functions f and g running from n to k and m to k respectively, then there will be a unique function here that will be written as the pair fg, making the triangles commutative, which means, so I'm referring to the left side triangle here formed by iota 1 fg and f, and the right side triangle formed by iota 2 fg and g. So the commutativity of these triangles simply means that the composite with iota 1 of fg is going to equal f, and the composite of fg with iota 2 is going to equal g. So there is unique such function in the middle. Now, another way to say the same thing is to say that the amount of functions in the middle is the same as the amount of ordered pairs fg. There is a one-to-one correspondence. But the sameness of this amount is measured by a very specific function of transporting the middle one to the ordered pair. And this we wrote out as a bijection from n plus mk. So this is now the set of all morphisms from n plus m to k, all the things in the middle. And the other set is the Cartesian product of set nk and mk, with this function being given by mapping an h, a morphism from n plus m to k. We map that to the ordered pair consisting of the tuple h iota 1, h iota 2. Now to say that this function, well, this is a function because for a given h, the composite h iota 1 is uniquely determined since iota 1 is given, and the composite h iota 2 is also uniquely determined. So this is a function from left to right. Now to say that this function is a bijection or one-to-one correspondence, we already know it's a function, that's important. Is the same as to say that for each element here, there is a unique one there that maps there. Now, picking an element here means picking an ordered pair fg. There being a unique thing here means there is a unique there, which maps there, meaning that the triangle is commutative. So to say that some random h maps to pair fg is to say that if I start off with pair fg, right? To say that h maps to that pair is to say that this pair equals that pair, which is to say h iota 1 equals f and h iota 2 equals g. I could have simply explained the diagrammatic condition without talking about the one-to-one correspondence, which makes things a little bit more confusing maybe. But the importance of this is that now if we count the number of elements in the left side and the right side set, in the left side we have k to the power n plus m, because that's how many functions we have from n plus m to k. On the right side, it's a Cartesian product, so the number of elements is this number times that number, so it's k to the n times k to the m. And because the two sets are bijective, these numbers will be equal. And then we get a very familiar formula for exponentiation. So we're basically unpacking the set theory behind this formula and using that as a definition of addition of objects in a category. So something very familiar, something very, very basic that comes from school, now suddenly becomes very advanced. Now, how do we set this up as a definition? Because so far we've been setting this up as a property of n plus m in this specific category net. We now want to give a definition of a sum of two objects in an abstract category. Well, it's just a very easy conversion from the property to the definition. And we did write this out. I'm going to write it out again. Given two objects N and M in a category, and this can be now any category, their sum, which sometimes is also called another name, but I'm not going to tell you the other name, not to reveal the surprise that's coming. I'm going to tell you the other name later. Their sum is a diagram of this kind, but now it's just an abstract diagram of objects and arrows. So when I say it's a diagram, I mean the data of a third object and two arrows connecting the given two objects with the third object, the way that's displayed on the picture. So this entire diagram is the sum, right? So the sum of objects is the entire diagram. It's not just the middle object. We need to know how to get there, how to get to the middle object, which is something we never did with natural numbers when we thought of it discretely, without any arrows between numbers. So the sum is this diagram, and the axiom that defines, that makes it into a sum. So I'm going to say now such that for any, and now I'm writing the same property we wrote out before. For any f and g that are morphisms, the way that I'm going to show. So for any f from n to k and g from m to k, there exists unique h from n plus m to k, such that h composed with iota 1 equals f, and h composed with iota 2 equals g. So that's exactly the same property we spoke of earlier. Now this definition has two such that, so it makes the whole sentence very complex. I'm going to put a block that separates them. So this is the block for our property. So the first such that indicates that we want that property to hold, and the second such that right here is just a part of the property. Addition of numbers is simple enough. This seems like important enough. Why don't we teach this definition to kindergarten? Who can answer that, by the way? That's an interesting question. What makes this definition not accessible to younger learners at school?
My sister wouldn't care.
Wouldn't care. Yes.
So I think children sort of think, they don't start to think abstractly. So it's better to give them something that is concrete if they have objects that they can work with. As soon as we start talking about abstract objects and arrows, they don't really understand what's going on.
Thank you. Yeah, Michaela, that's a nice way of looking at it. I agree to you to a great extent. However, we should not forget that numbers already are abstract. And we kind of still manage to teach numbers because for every single number, we give them lots of examples that manifest that number.
I think that it's simpler to understand to a person who wants to understand, but we would first need to figure out a way to get children to want to be interested before this would be a simpler way to teach it to them.
Look, I mean, in my experience of teaching, I mean, I've heard of this argument from many other lecturers that students are not interested in something. I've never ever met a student that's not interested in what I was talking in class. I haven't simply met them.
I used to try and help my sister with her maths lit homework. She wasn't interested in understanding how straight line graph works.
But maybe it was the approach of it's appropriate teacher to force. So you shouldn't force a child anything, I think. But you can kind of detect what they're interested in, and once they're interested, then start talking.
She was interested in getting her homework done.
Sure. Now the question is, what? So there are two reasons that we pointed out. One is abstraction, the other is in interest. But are these the only two?
I think also, I mean, even in second year, most of the people studying math struggle to comprehend the epsilon delta definition of a limit.
Yeah.
And it has to quantify the same way quantify structure existence.
So the third reason, which I personally think is the biggest reason, is the logical structure of this definition. This is a very complex statement, logically complex, and we're not used to these kinds of sentences in everyday language.
It also is simple once you already have a reasonably well-refined definition of what a map is. So like when you spend time thinking about maps and understanding what they are and how they work, then this is reasonably simple. But yeah, especially at a school level, people have such a bad idea of as to what a function is and what a map is, and they wouldn't really have much.
So, okay, so you think that after we already know what a function is, then it's easier.
Well, once you've spent, I think even more than knowing what one is, having spent time using them and working with them. So you have like when you say this is a map, I have a pretty good idea as to what you mean because I've dealt with it. I've dealt with them. I've like worked with them.
Right. Okay, so let's test your theory out.
Oh no, it's scary, no.
You're saying that actually the structure of that definition is not so complicated after we already know what functions are, and we're going to
now get a question on about a map saying I know what one is.
You're going to check that immediately. We defined sum of two objects as a certain diagram. Now, one thing we know about natural numbers that's very important. Take 2 and 3. 2 plus 3 will be 5, but it will not be any other number. So the two facts, one is what its value is, and also the fact that it's unique. Do we know that the sum of two objects in a category will be unique? So what if I had two of them, two candidates? One is the usual one we know that must be there, and the other one, something else, which possibly also maybe behaves like a sum. We're going to call it S, which has its own two functions. Let's call them I1 and I2. This is the one that we know, iota 1 and iota 2. Will we be able to prove that S must equal n plus m?
It would depend on the functions, right? The I1 and I2.
So what we know about this diagram is that, first of all, we know that this thing is a sum. And we are also told that the other one is a sum as well.
The exact same sum, or just need some sort of criteria that we have on what a sum means?
Okay, now you see, your question is already going back to the complexity of the definition. If you examine the definition carefully, the sum is defined for given two numbers. In this case, the two numbers that are given are n and m. So I should actually say it's sum of n and m. And the other one was also given to be the sum of the same n and m. Does that guarantee that S equals n plus m. What if we find that there is another number here, still in the category of natural numbers, that fulfills exactly the same property? Then it would have been a bad definition what we did, right?
Are we saying both kinds of work for the same kind of sum?
Yeah. So what? There's only
I
one kind.
think an addition like 3 plus 5 will be 8.
No, now we're using this sum. So we're now working in an abstract category.
Yeah.
And we're using the sum of two objects in a category the way we defined previously.
Because in the previous one, it's based on what the iota 1 and iota 2 means.
Sure, sure.
It's just like a kind of union.
I think that I'm
Sure. So, but remember, the previous definition was a definition. It was no longer. This is no longer something. This definition is no longer something happening in the category of natural numbers. We observed something that was happening in the category of natural numbers, and we abstracted from that to a general category.
So actually, maybe then what I want to ask in this definition is iota 1 and iota 2 like specified? Because from the diagram, maybe this is a part where I'm confused about. I feel like we managed to define addition because we said iota 1 just is like an identity type of thing, and iota 2 just add like unions with the other set. And then
Right. Now you see, that's exactly what I meant when I said that the sum is the entire diagram.
Yeah.
So we must be given iota 1. We don't know what it will be in advance. We must be given iota 2. We must be given n plus n. So we have to be given a data of three things.
Okay, and then maybe that n plus n m in the middle there is
Just notation.
yeah, that's just
Yeah.
that's not that doesn't mean like the plus the
No.
yeah.
No, it's just a kind of quick way of introducing notation along with the definition. Otherwise, I would have written an S there, let's say, and then after the definition, given a remark. In the future, we're going to write S as n plus n.
Then I would guess that it wouldn't always be addition. It depends on what iota 1 and iota 2 is.
Well, it does. It does depend on what iota 1 and iota 2 is, but remember that there is a property attached to it. Even if we change iota 1 and iota 2, it could still be that this object is
But
the same
isn't
object.
the property that we're attaching just commutative.
Commutativity of the triangles. No, not just that. It requires possibility of creating these middle maps out of the given ones. So you see, it's familiar with functions is not enough. This definition has a very complex structure. So not only we don't teach this at the school level, we don't even try to teach it at an undergraduate level sometimes. Sometimes we try it. Yes.
So, for teaching to kindergartens, can't you start with that picture there, and then as the years go on, you introduce? So in kindergarten,
Yeah, that's a good idea. Yeah.
kindergarten, you just focus on the intuition, and then you use pictures and simple.
Because you do in that.
That's a good idea. Yes. So Liana has some strategy how we can develop a curriculum so that after 3 years of teaching kindergarten children, we can at the end of the third year arrive to the definition of the sum of the objects in the category.
But I think you can probably also teach, even if it is a complicated structure, like I would think if it's repeated enough and you give like concrete, you kind of alternate concrete examples.
Yeah.
And
You said a good thing, repeat it enough. And because we had to repeat this, I repeated it now already the fourth time, I think. And probably we'll have to repeat it a few more times before we can solve this problem.
I think that for kindergartens to get this, they won't be as good at doing multiplication and arithmetic as we were when we
Okay.
got to.
So I just want to make something clear. So the purpose of these lectures is not to discuss kindergarten. I just use it as a temporary diversion. But let's go back to university. Here's the question: we could potentially have two different sums. Will we be able to prove they're the same? Carla, you think we won't be able to prove that? You haven't even tried.
I have a counterexample.
Oh, you've got a counterexample. Okay, what's your counterexample?
So if you take again the natural numbers as objects, but you also add, you just add the sets 1 to n. You also add like translations of that, like 2 to n plus 1 and 3 to n plus 2. then you have many different sets with n elements, and then any set with n plus n elements will satisfy the sum.
So let's do that. So I'm going to take a specific example to illustrate what you're saying. Shall we make n to be 10? And let's say we make m to be 5. And so this is our 15, right? This is because this is the usual sum. And what would you put here in the place of s?
2 to 6.
Sorry?
2 to 6.
2 to 16. Okay, we're not allowed to do that in the category of natural numbers. In the category of natural numbers, remember, objects are natural numbers. They're not the sets. If we go back to the definition of this category, here objects are the natural numbers, not sets. And this, by the way, answers a question that was posted here in the chat. And I also want to take the opportunity to welcome Alexander Janelidze. Alexander, are you joining us from Georgia?
Yeah, exactly. Hello.
Welcome.
Thank you.
So he asked here whether wouldn't be better to not just use the sets 1 to n, but arbitrary finite sets as objects. We could have, but we didn't do that. Okay. So that kind of breaks your counterexample.
No, but that's what I was suggesting. So if you in a different
But
category.
in a different category,
Yeah.
yeah. In a different category where objects are not natural numbers anymore, they're just finite sets. Carlyle is saying that this bottom diagram would still have the property of sum, but then we see that these two sets are not the same. They're not the same, I agree, but they have the same number of elements. And for the sake of counting, that's all what matters. So, can we express the fact, by the way, that two sets have the same number of elements in the language of the category that we're working in? It's bijection. But can we express bijection in the language of the morphisms of the category?
Yeah, but again, this again for the first one.
Right. So I will have morphisms going back and forth with very special property that going forward and then backward gives me identity map, and also the other way around. Is that fine for everybody thinking of bijections this way? That we have back and forward map where each composite on each side is identity map. So maybe we won't be able to prove that n plus m is equal to s, and indeed we can't, because in this example you see it's not, but we might still be able to prove that the two objects are isomorphic to each other, which is a term for bijective in a general category. So will we be able to find, going back to the general picture, will we be able to find maps back and forth here, knowing that the top side and the bottom side, both of them are sums?
Yeah, yes.
How?
Well, each of them have a unique map between K and the sum. So if your sum has a unique map or unique bijection to K, both of them have a unique bijection to K, then you just can compose a composite bijection, I suppose.
Okay, so you're saying, I think what you're saying is that because the top diagram is a sum, by the definition of sum, and if we go back to the definition of sum, we're told that when something is a sum, like here, when this top diagram is, that means that if I have any other K and any two arrows, they will produce a unique arrow in the middle, making the triangles commutative.
Wait, did we say that FG map is a bijection? Not restate that, no, okay.
So, okay, so but are you tracking what you suggested then?
Well, if we don't know that that's a bijection, then I still think I'm right, but I don't have the right to say it.
Okay.
Like, I think that that's a bijection, but we haven't stated it yet, so then I think I'm
No,
right.
I mean,
but
this in general, this middle map doesn't have to be a bijection. You can have K to be a one element set.
Okay. Oh,
And these are F and G are constant functions. And then the middle one will also be constant function. But there is something kind of symmetry in this diagram where the top part of the diagram and the bottom part are similar. And so if I remember that and I go to the next page, I can see here that I've got actually the same picture. This picture is very, very similar to the one we used to define sum. By the definition of sum, I1 and I2 will create a certain map, a certain function. When I say map, I mean a function and vice versa. So there will be a unique function here, which we write as the ordered pair, I1, I2. Don't you agree with that? It's the unique function such that this composed with iota 1 is I1, and it composed with iota 2 is I2. Do you agree with that, Matt?
Maybe.
So let's go back to the definition of sum, and let's read it carefully one more time. So it says, given two objects n and m in a category, their sum is this diagram, such that, okay, what is the property? For any f and g, there exists unique h, such that the composites are that and that. So for any f and g, there exists a unique thing here, which we write as an ordered pair, such that this composite is f and that composite is g.
Yeah. Yeah, I'm stuck on, sorry, the definition or of iota 1 and iota 2.
So there is no definition for iota 1 and iota 2.
Yeah, or how they're supposed to.
We don't know.
Yeah,
But in a general category, we don't know what they're doing. All we know, whatever they're doing, the effect of their doing is this property.
Yeah, but what I want to, like, what I'm still not clear on is somewhere where we define like union of two sets, or somewhere we're saying that this is the operation that we're doing. Yeah.
You mean on this picture?
Yes.
Okay.
Yeah, where is that in that picture?
It's gone.
So we don't necessarily need to know that it is a union number.
No.
Okay.
This is an what we have in this definition is an abstraction. So the question you're asking, if you forgive me for the analogy, is a bit like this. I explained what is 3 by saying 3 apples is 3.
Yeah.
And then I show 3 houses, and the person comes back and tells me, you must be crazy. These are not apples. So
I understand the abstraction there, but I'm now just wondering, so you're then saying this structure on the left, this kind of abstraction, it uniquely captures addition. Like, I'm still trying to be sold on that.
So at this point, we don't know that.
Okay.
We are trying actually to prove that it uniquely captures addition.
Yeah.
So what we did so far, that's something we did last time. We proved that if I put here the usual sum, in other words, this kind of union that we spoke of, and the iota map, iota 1 and iota 2, I choose in a very specific way.
Yeah.
Then this property holds.
Yeah.
So I know that the usual sum satisfies the condition. But there could be many other things that satisfy the same condition.
Yeah.
It doesn't mean that this is a good abstraction until we can prove that this definition determines the sum uniquely in a suitable sense. Do you agree with that?
Yeah, no, that's.
And now we're doing exactly that. We're trying to establish in what sense is this notion of sum unique?
Yeah.
So do you agree that if I have one sum and then another one, so displayed at the top part of this diagram and the bottom part, then because of the definition of the sum applied to the top part of the diagram, I'm going to have a unique map and from n plus m to s, unique under the property that the triangles commute. I'm not saying that there's only one map from n plus m as altogether. Just under the property that the triangles commute.
Yeah, and that's by definition.
Yeah, by
And the
definition.
same the other
And the
way.
same the other way around, exactly. So we're also going to have something going backwards here, which will now be for the other sum. So this will be the ordered pair consisting of iota 1 and iota 2. Okay. And now let's see what happens when I compose them. Do I get this effect that if I go this way and go back, I have an identity morphism or not?
Yes.
If I get that effect, that it would mean that these two objects are maybe not equal, but they're kind of almost the same, because it's possible to go back and forth without loss of information. So to investigate what happens to this composite in each direction, and you probably agree with me that it's sufficient to just prove in one direction, because the other one is just any other sum, so the same argument will apply on the other side. We're going to do a diagram for that. Sorry, maybe I want my diagram to be slightly of a different shape. Now I want to put this S in the middle here, because I also want to put a second copy of n plus m. And it will become clear in a moment why I want to put second copy. Because I want to show these arrows in the diagram of composable arrows, so that I can maybe use some geometry of the picture to help me with the proof. So the first one, the first middle arrow was the pair iota 1, was the pair I1, I2, right? Was the arrow given by the definition of the top part of the diagram, and then definition of the middle, so definition of sum, to be more precise, applied to the middle part of the diagram gives me here the pair iota 1, iota 2. And now I'm interested in this composite. I'm interested in the composite of the pair iota 1, iota 2 with the pair I1, I2. That's the composite I'm interested in. And what do I want to establish about that composite? I want to establish that that composite equals the identity of n plus m. That's what I wanted to establish. How will I establish that? Let's draw the identity in the diagram as well, so we can more easily compare. So the identity will also run from n plus m to n plus m, right? Here.
Have a unique one between n plus m s and s and m. So it's only one composition can only be one thing.
If I go back to the definition of sum, notice here that this unique arrow fg can be, I mean, it exists, not can be, that it exists for every value of k. For a different k, there will be other arrows. So we can always change our k. So how does this apply to what we have here? Well, we have two possible k's here. One is s, and the other is n plus m itself. What happens if I apply the definition of sum with this n plus m, the bottom n plus m being in the place of k? then I know there is unique error here, which makes the triangles commute. So, and that unique error would actually be called the order pair iota 1, iota 2, right? This will be a different order pair to the one I already have on the diagram, because the one I have on the diagram was created out of S being the sum. That's a different sum. This is out of n plus m being the sum. So perhaps I should use slightly different notation here so I don't confuse these two errors with each other, because this S was a sum that's different from n plus m, possibly different. I'm going to call this, I'm going to use different types of brackets. Instead of round brackets, let's actually switch to using their square brackets. Okay. And the property that defines this uniquely, this orange arrow, is the commutativity of those triangles. In other words, the fact that this iota 1, iota 2, composed with iota 1 equals iota 1, and iota 1, iota 2 composed with iota 2 equals iota 2. So I'll give you some time to think about what I wrote there while I fix the other round brackets as well.
Oh.
So this system of equations are the defining equations for the orange arrow. We know that by the definition of sum, there is only one solution to this system of equations. I mean, that's another way of thinking about the definition of sum, right? Let's go back to the first definition. In terms of, in the language of solution of a system of equations, I could have said here that I'm going to add this in other words, the system H composed with iota 1 equals F, and H composed with iota 2 equals G, has a unique solution. HUS means has unique solution. So going back to what we're working with here, that unique solution is the one that we write as ordered pair, right? Now, I have two arrows here that I want to compare, the identity arrow and this composite. I want to prove them to be equal to each other. If I can prove that both of them are solutions of the system, then they will have to be equal because the system has unique solution. So let's do that. Let's prove that both of these, left-hand side and right, both of them are solutions to the system. One of them will be easy. If you plug in here the identity arrow, you easily see it satisfies both equations. Why is this also a solution? Now we'll have to do a bit of calculations. So let's check that this composite is also a solution of the system. So I'm first going to check that it satisfies the first equation in the system. So I've got iota 1, iota 2, composed with I1, I2, and that whole thing composed with iota 1. I want to calculate what this is. I want to prove that that composite will equal iota 1. What will be my first step of calculation?
In the brackets.
Yeah, we can't simplify the left-hand side any further. I mean, that's the whole point of this exercise is to see what that left-hand side is. We can't simplify it further, but we can use associativity to move brackets from left to right. So we're now starting to use some axioms from the definition of a category. So we get this. What do we do after that? So anyone from online audience would like to help us with the computation that Carlisle already has figured out?
From the top triangle, we have that I1, I2 composed with iota 1 will be I1.
Thanks a lot, Daniela. I completely agree with you. So remember that one of the defining equations for this arrow, which I'm going to mark with yellow now, is the commutativity of this triangle, again marking with yellow. But what is the commutativity of that triangle equationally? That it's exactly that this thing here equals I1.
So the bottom triangle on your diagram, isn't it supposed to be L1, L2? It looks like you have two L2s, or you go to two. Yes. No, your F and G maps. Best.
The one
the one you're pointing at. Isn't that supposed to be L1?
Iota.
Or iota 1?
Yes, it's supposed to be 1. Yes. Absolutely, you're right.
How long has it been then?
Quite a while. Quite a while.
Concentrating, right?
Yeah, it shows we're really concentrating. Yes.
I only noticed it because now you have to follow the diagram.
So we know what to do now with the right side of that composite. And we're going to do that to it. So in the place of that composite, we can now write I1. And then the next step, probably the next step now is
Easily equal to iota 1.
for the sake of completeness, let's also highlight that. So we also know that triangle commutes, which would make that composite there equal to iota 1. And that's exactly what we wanted. And I guess you can easily believe that if I had iota 2 here, the computation would be exactly the same. It will now be using the right side of this diagram. Now, there is a geometric way to do this computation without writing anything down, just following the diagram. So if I go back to the diagram and I'm going to draw something, not because I'm supposed to draw, but just to show you what kind of drawing you do in your mind when you do the geometric computation. So you don't draw this on the paper, you do it on the mind, but to show you what I'm doing in my mind, because we don't have yet telepathic abilities, I'm going to transport it on the board and draw it. So in my mind, I'm thinking, I want to prove that iota 1 composed with this orange arrow is the same as iota 1 composed with that composite, where the orange arrow for me now is the identity. Okay, so now I want to investigate what is this iota 1 composed with that composite. Well, it's this and then that. But this part is the same as that. So every time I draw this blue arrow, I'm tracing something in my mind. So because this is the same as that, this composite will be the same as that composite. And because this composite is the same as that, overall we get that this composite is the same as that. And exactly the same works on the other side. This composite is the same as this composite because of the upper triangle, and then the same as that. And the same is true for the identity arrow, if I put identity in the place of orange, and therefore these two arrows, this one and that one, must be the same arrow by the definition of sum applied to this diagram. So both this orange composite and the identity arrow are solutions of the system, and because the system has unique solution, they're equal. Any questions on this? If it was something unclear, please do ask, either online or in person audience. It's easier for me to track that everything is understood
Maybe check
at the
the chat.
in-person audience, because I can look at them. So this is list of participants, and what about chat? There's nothing in the chat, so I assume that everything is fine, or is it not? Let me ask someone here. Maybe Michael. Hi, Michael.
Isn't Michael the one that you muted earlier?
We can unmute.
Would you like to say something, Michael? Okay, maybe that wasn't a good idea. Maybe Michael is not around at the moment.
So if I have any problem or that I can encode into the structure, then I automatically know that I can use addition, that like with natural numbers to that there's like an isomorphism, or there's an equivalence to just like natural numbers under addition. So if I find this structure on like any kind of thing, then I know there's a direct mapping to just something.
If you're in the category of natural numbers.
Oh, so that. Oh.
There's an analogy to addition, right?
The general sum of objects in a category will have many properties that are shared by addition, but there will be many others that are not. This is a more abstract notion.
So our objects, are you saying our objects needs to be whole numbers?
In order for this to become actual addition of numbers.
But so if I have chairs or something, but like the way that I'm thinking about my chairs adheres to this structure, doesn't that mean there's just a one-to-one mapping to each chair in a natural number?
Yeah.
So I can use that to solve my chair issue.
Sure. Yeah.
So, okay, will there at least be, so in a similar way as to what we can sometimes think of less than and greater than, like we do with subset relation, like in the sense of like the ordering or whatever, do you at least have that kind of addition and addition analogy going on if we have this structure?
Yes and no. So once again, depends on which category you are. In some categories, additional behavior is similar to the addition of numbers. In others, they won't.
So there's if we're saying our objects needs to be natural numbers, but it's, there's no structure of addition on the natural numbers, or is it kind of like it's natural numbers with addition?
There is no structure of addition a priori. We started off with a structure of arrows between numbers.
Yeah, so the arrow between 5 and 6. But because of this, the 5 is just a label for a thing.
Yeah.
So So why are we then saying it has to be?
So you're asking a similar question to Alexander, who was saying that maybe our objects can be not just the specific kinds of sets, but also any other finite set. And yes,
or any. thing.
Or well, if it's anything, then we still need to describe what arrows will be between them.
Yeah.
But yeah, that's the whole idea of category theory, that you can turn your objects to be anything and then transport the constructions and the notions and theorems and stuff to the other things.
A question I probably should have asked earlier. Is 0 a natural number in your opinion? Meaning at least as far as this course is concerned?
Yeah, it is, yeah. So what have we actually proved here? Let's first look at what we proved here. We proved the following theorem, that in any category, sum of two objects is unique up to an isomorphism. So an arrow having the property that has a reverse arrow, such as the composites there and there are identity arrows, is called an isomorphism. We haven't defined it yet. We will do that, but if we have that notion, then this is what we proved. Now, in the category of natural numbers, in this specific category of natural numbers, where objects are natural numbers, when will two numbers be isomorphic? If they're equal, because, yeah, it's clear, right? Because the number is given by the set of 1 to n. If there is a bijection between them, the amount is the same, so the numbers. So this theorem applied to this category proves that addition is actually unique up to isomorphism, but literally unique. However, it's only unique in this ingredient. I could have set up my iota 1 and iota 2 in a different way. How? Namely, if I go back here, I could have recolored this middle thing by scattering orange and green, mixing it in between each other. I don't have to map them specifically this way. And this fact has to do with the fact that I think I lost the theorem. Oh, here's the theorem. Sorry, I wrote the theorem in the wrong spot, maybe. This has to do with the fact that the middle object here will have a lot of isomorphisms going from here to itself. And if you take these iota 1 and iota, you compose them with the isomorphism, so you're reshuffling the elements basically here. You will still get a diagram that acts like a sum. When you explain, basically the conceptual thing behind this is that when you explain that you can get sum of two sets by, you can get sum of two numbers by combining the sets. The order in which you list the elements of that set doesn't matter. You know, list the first elements of the first set and then elements of the second set, or mix them around. Okay, so now going back to what we wanted to do last time and we didn't do. Is there a way to capture? So we kind of figured out a way of capturing addition of numbers, and the question is if there is a way of capturing multiplication of numbers. Once we figure that one out, then maybe we should go back to the category of matrices and see what addition and multiplication give there. So let's try to invent something similar for multiplication. If I have here n and m, and I want to put in the middle n cross m, let's use also a set theoretic drawing to inspire us what the condition should be. So maybe n is a 3-element set and m is a 2-element set. How do I draw the product?
The Cartesian product.
Well, maybe that's the first part of my question. What is the product of sets that corresponds to multiplication of numbers? The answer is Cartesian product. But then, if we know that, then do you know how to draw a Cartesian product of sets?
You draw an arrow from each arrow to each other arrow.
No, you draw a matrix. And then to make the drawing more suggestive, I'm going to draw one of the sets as an x-axis, and the other one remains vertically aligned, so it's y-axis. Okay? So we basically put these dots here and there. So this is my orange part. And then the green part is here. And then I form points out of points whose coordinates are given by the orange dots and the green dots. If I want to do something similar to what we did with addition, we will probably be looking for a way to connect n with n cross n, and also m with n cross n. Can we connect them in any way?
Well, the number of elements in a Cartesian product between an n coordinate set and an m coordinate set is n times n.
Sure, but we want to connect them with an arrow, like we did last time. We want to try to copy last time as much as possible. You know this joke about a physicist and a mathematician.
That set's quite infinite.
Well, there's one joke about the boiling a kettle. So they were both shown how to do that. You put water in a kettle, you put it on the, what is it called, stove, and you put it on, turn it on, and then it boils, and then you take it off. And now to test the understanding, they gave them a kettle which already has water. So the physicist thought, okay, it's already has water in it, so didn't fill it with water anymore, he just put it in. Now, what the mathematician did, he emptied water out, he emptied the water, and then he put new water in. And they asked him, why did you do that? And he said, because I wanted to reduce this problem to the previous one.
Well, yeah, we kind of want to, I'm thinking about it explicitly, we want to just get like ordered tuples of the one. Like n should go to the first index and n should go to the second index, and then just all the.
Okay, so if I take an ordered pair, which is an element in the middle,
Yeah.
it can be mapped to its first component on the left side and the second component on the left, right?
Yeah.
So we actually have maps this time going the other direction than what we had previous time.
Okay.
And we're going to call them pi1 and pi2 because they're projection maps.
Oh, that was going to be my question.
Yeah. So the projection on the y-axis and the projection on the x-axis, if you want to put it this way. Now let's insist on doing something similar what we had before. So we take a K and let's draw two maps. Before these maps were running this way, right, from N to K. But we reversed the iota maps, so maybe we should also reverse these ones, right? So let's say we've got these maps in reverse. Let's call them F and G. And the condition should now say that there is a unique map here, unique H, that makes the triangles commutative. And let's draw that as a column, as a pair, but written in a column.
Is there like maybe a very simple, why do you say that makes the triangles commutative? Does it relate directly to like commutative of like A times B is the same as B times A or whatever?
Yes, because you can, if A and B are end functions, then you can represent commutativity of that commutativity as commutativity of this square. A composed with B is the same as B composed with A.
Yeah.
That's the origin.
Okay.
But here it has nothing to do with, for the triangle, it has nothing to do with ordinary commutativity.
Okay, so it's
Yeah,
not that's
but
it's
it-
not a property, but yeah. But we need a square.
To recapture, so one of the things category theories do, they reinvent the terminology for everything.
Okay, now I just wanted to make sure.
Starting from the term category, which actually meant something in philosophy. Something quite similar, by the way, to what it means in category theory, but
Still mean that.
yeah, it still means that in philosophy.
So what do you call commutativity, like mathematical, the other like group theory commutativity and category theory of this commutativity means something else?
There is also a third version of commutativity that comes from universal algebra, which sometimes is called interchange law. Imagine you have a matrix of values and you're operating in this direction and also in that direction. So in this direction, it's a binary operation. You can operate on these two or these two or these two. Vertically, you can operate with a ternary operation. Now imagine you operate with binary 3 times and then once ternary. That ends up being the same as operating first with 2 ternary operations and 1 binary. Then we will say that these 2 operations, the ternary and the binary one, commute with each other. And again, usual commutativity can be reduced to this kind of commutativity. So that's another, but which can still be expressed as commutativity of a diagram.
To be fair, considering the points of the diagrams almost to try and show that the objects are the same, it's kind of apt that you call it commute, that they commute anyway.
Yeah, so the idea is that, I mean, commute also means something in real life, right? For instance, I was commuting from Stellenbosch to from Cape Town to Stellenbosch for many years before I moved to Stellenbosch. And so I was taking a certain route, but then on a different day, if I get bored, then I take another route. But the result is the same. So commutativity of this diagram means that this composite equals that composite. In our case here, we're saying that this FG would solve the equations that I'm writing now. So the first one says that this middle arrow composed with pi1 equals f, and the second one says pi2 composed with the middle arrow. I should have actually said them in the same order to be consistent equals g. I just tried to repeat the same condition. I have no idea what it's going to do. Will we actually be able to prove that this system of equations does have a unique solution when my pi1 and pi2 are projection maps?
How do you perform pi1 on f when f's codomain isn't pi1?
So we're not performing pi1 on f, we're performing pi1 on the
sorry, okay.
On the FG. So let's prove that indeed there is unique arrow from K to N cross M making the 2 triangles commutative. So let's call it temporarily, let's call it H. I'll pick an element from K, H of X. First of all, I mean, as you know, in general mathematics, when you want to prove something is unique, you need to prove it exists. And then you need to prove that if there is a second one, it equals the first one. So let's first prove that it exists. Will I be able to define h of x in such a way that when I take its pi1 and its pi2, it ends up being f of x and g of x? Well, I basically defined it, didn't I? I want to define h of x in such a way that when I take its pi1, which is taking the first component, equals f of x. And when I take its pi2, which is the second component, equals g of x. So I'm basically defining h of x to be the pair fx gx. So we have a proposal. Does this h of x make those equations hold? What is pi1 composed with h of x? Well, according to this definition, clearly it's f of x. And the same for the other one.
That is so much cleaner than the way we did this in 378.
Because we did it.
No, we did it with like some or statements and stuff. But this is a bit way better.
Okay, so we know that H exists. How do we know it's unique?
Oh, we already I mean, we started with an arbitrary H and then concluded it must be that.
If I have an H that makes this commutative, in the pair, the first one must be f of x, and the second must be g of x. So the formula is forced by the fact that these two equations need to fall. So it works. So what is remarkable here is that just by reversing the errors, we now switch from addition to multiplication. I mean, we knew this kind of, right? Because we write sum like this and we write product like that. So we kind of knew that. Actually, we didn't know that. We had no idea of that. Yes.
If we're dealing with the category of natural numbers, would the product being 12 be in the product set, I suppose, 3 times with the pair 1, 12, the pair 3, 4, and the pair 2, 6? Or is it only there once, but you can represent it in those 3 different ways?
What are the 3 different ways?
Well, so 12 is a product of 1 and 12. It's a product of 3 and 4, and it's a product of 2 and 6.
Yeah.
So if you wanted to represent 12 as a product, can you represent it equivalently as those different ways? So I suppose in the set B of the product, would it be there 3 times as all the ways you can get it, or is it only there once and you can represent it equivalently in different ways?
In our category, remember, objects are natural numbers.
Yes.
There's only 112 in the category.
Okay.
So the answer is only once.
Okay, but then in the category.
But in an abstract category, if we were working in an abstract category, if there were many versions of 12, like different sets of having 12 elements, then I take the product of 1 and 12. And then when I take the product of 3 and 4, I might have chosen a different one. In fact, I would have chosen a different one if my picture was right, because this will be set of ordered pairs and that one too. Both of them will have 12 elements, but there will be different sets of ordered pairs.
So then the n cross m, does that not always get represented as a pair like you have it there? So you have h at hx as
But this is only after I have chosen a very specific representative for n cross m to detect some specific object in a very specific category, the category of natural numbers. And by the way, sorry. So let's actually go back here. So what we said here is actually wrong. This doesn't work in the category of natural numbers.
Okay, interesting.
Because I think that's what you're maybe saying.
So I was wondering if h is always equal to a pair, then how are our natural numbers represented as products?
Exactly. Yeah. So thanks for that chat. So if we consider the fixed version of the category of natural numbers, the one that was suggested now by Alexander and Carla and also Matt, where all finite sets are objects, then what we did here is fine. But in our specific category of natural numbers, the set of ordered pairs is not allowed. All sets are numbers from 1 to that number. So we need to first redesign, right? So we have to reformulate this definition. We have to kind of encode the set of ordered pairs as a string. So what would the formula be in our case? So we could go like this: 1, 2, 3, 4, 5, 6, right? So what's the formula?
You get just the one number.
Yeah,
Am I allowed to use like exponentiation and things?
yeah.
Okay. So it would be, I think, I don't remember the example, but something like you would have two.
So if we do it like this,
Product of their primes, I don't know.
1, 1, 1, 2, 1, 3, right? So we're looking for a general formula for AB. AB gets mapped to what?
I want to say A times B, but that would give you problems.
It's probably a modular and floor thing.
Isn't it A times n minus 1? So which one is, yeah, n minus 1? So I might be wrong here, but we can start with that. Plus B? Isn't it that? Would that work?
What would N be?
Why did I say n minus 1? Sorry, I meant to say a minus 1 times n.
What would N be?
N is good. N. Okay.
Isn't it this? But maybe it's the other way around.
We were starting from 0, so it wouldn't just be AN. Why is it A minus?
I think it should be the other way around, right? According to what numbering I did on the picture, it should actually be the other way around. So it's B A times A plus B minus 1 times M.
Are we restricting A and B to not be 0? Or at least B then? Because then if B is 0.
No. Sorry, I'm making a mistake again. But it's because you're not helping me. So I'm just stupid for this. You need to tell me what should happen there.
I don't think I'm understanding. It should be A plus
B times N. Oh no, B times N, yeah.
So we want to go, we want to decide in which column we are and in which row we are, right? We decide in which column we are based on B. That decides in which column we are, right? But we are incrementing numbers also column-wise. So while, let's say, we are in the first column, I should be stepping with A. So doesn't that mean that it will be the formula I wrote before? A plus B minus 1 times M?
Why B minus 1 is B can be 0?
B cannot be 0.
Why not?
Because N, we think of N as the set from 1 to N. Yeah.
But that should be N, shouldn't it? Because N is that.
And that one should be N, that you're right, yeah.
So it was right.
No, both of them were wrong, right?
No, the previous one you had was N.
Oh, was it? Okay. I meant to write.
Still don't understand.
Well, we can test this out, right? Let's actually test this out. Let's go back to a blank page and let's do maybe a bit longer example. So I want to encode this thing as a set with 12 numbers in it, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the pair AB, which will be a random point here, let's say this one, will have label, I want to get to 7, right? So it's in the second column. So I must pass all these numbers. And remember, the number of these is n, and the number of these is m. So I must pass all of them, but I must do it once, and then add the 3. The 3 here is so maybe what I did bad there was to use the first coordinate to represent the y-axis. That's also what's contributing to the confusion here, probably. But anyway, so A is the one that goes 3 steps up. It's a weird way of thinking about ordered pairs, but that's how we pictured it originally. So we're using twisted ordered pairs here. A is the one that goes up, and it goes up by 3 points. And but across it, it goes only 1 copy of n, and that 1y because we're in the B coordinate being 2, which means that this copy hasn't finished yet, so we have to subtract 1 from B to see how many of the top whole n's will fit there. So that's how we end up with A plus B minus 1 times n. And now we can test this to be true or not. If I put here 2, 3, no, not 2, 3, sorry. It's 3, 2. With this twisted coordinate system. If I put the 3, 2, I'm going to get 3 plus 2 minus 1 times 4, which is equal to 3 plus 4, which is 7.
We wanted to really show that there's going to be also get the inverse of R.
So what I'm trying to say is that if we want to work with this more primitive category of natural numbers that I originally proposed, and we don't want to step out of that category, then we actually should have said here, this unique H shouldn't be defined this way because this doesn't make sense. It should be defined a different way, which is this way. This is how it should be defined.
Yes.
And now I still need my formulas for pi1 and pi2, and then I'll be doing a lot of calculations modulo something here.
To be n again.
Yes. Yeah. Yes, Matt, I'm listening.
Oh wait, no, I see. I think it is the.
But if you don't really
Okay,
feel
no,
like
I see. Okay, no, I agree with your problem.
if you don't want to, if you don't feel like doing the calculations, can't you just say declare pi1 as a such that a plus whatever equals a number?
So I think at the end of the day, maybe Alexander gave us a very good suggestion to work with a slightly more expanded category to replace numerical calculations with basic set theoretic constructions like Cartesian products. Yes.
Can I give a generalization of that formula?
Yes.
All right, that's like this is just what I.
Generalizing to the n to the n.
Yeah, for like now I was just trying to think if we have multiplication of like more, not just 2 dimensions, 3 dimensions, 4 dimensions, or whatever dimensions. So because we have, let me just think.
You want that brush there.
Okay. So this is a 3 by 2 matrix, one way of looking at it. Okay. And this is the 3 by 2 by, well, this is like an order 3 tensor. So it's like a 3-dimensional matrix. So this would be like we had our A, which is the range, which would be now 3, and then B would be 2, and then maybe we can have C. These are indices. 3 times 2 times 2 is 12. So this would be the number 12, right? I'm just going to start numbering from 0 and go up to 11. And then I think the general formula is something like, you have 3, you have to specify where you are. So maybe you have an I, a J, and a K. Actually, I should maybe number that, but I think you have something like you enumerate over K, and then you do like, I just need to remember here. You have, this is not B times J. A, B, I. So I think like the general thing, so yeah, do you kind of agree with that? I think so. And then the general thing, if you have like I0, I1 to IN things, and then these would be all prime numbers, you'd have like P1 to PN. Just over.
So what are you using prime numbers for?
Well, this is just I'm just actually ABCs. This is the factors of prime numbers, right? No, this is just the factors. But if you had a canonical form, you'd make these prime. Okay, because that would nicely represent the 2 n minus 1 times your first index plus. And then this kind of just continues where you're just going to take, oh, sorry, this one is just, it's first just going to take, yeah, P1, and the next one's going to be P1 times P2 up until you're down with the last one, which is just 1. Okay, and that flattens the structure.
Yeah.
Okay.
Now let's turn this into category theory. So what you're alluding to here is that we can define a product of not just 2 objects, but also multiple of them.
Yeah.
You're coming up with a formula for that, proving that it satisfies the corresponding property. So if I had many objects, and let's write them this time, let's write them your way. Okay. So I will be, maybe, let me switch back to the other way. It could be just -1s here, right?
That's right.
Yeah. So if I had, let's say 3 numbers, A, B, C, their product, A cross B cross C, but now I should maybe write this as a general A I, and the product of the AIs, where I runs from, let's say 1 to R. Can we make that R?
Matt, I don't think your formula is quite correct. I'm not sure how to fix it, but C needs to be in the formula. Otherwise, if C is very big, then you can end up in the wrong branch.
I don't think C needs to be in the formula.
It kind of automatically cancels out in the end.
You see here, M wasn't in the formula.
So I'm just thinking if C is really big, right?
So,
you can.
So if C is like 100,
Yeah,
and A is 2 and B is 2, then you're gonna
So if
your picture becomes like this thing, but there's like 100 little things here. So going from this click to this click, there's going to be 100 numbers here, and then you need the you need the factor of this number. You're going to go from 101, 102.
So if you're in the second click, right?
Yeah.
And you're in 221, then that formula is going to be much less than 100. You're going to be at the 101 thing.
So yeah, let's see, because if I'm in the
You aligned the missing factor with the coordinate, but remember the other formula, it wasn't aligned. The b minus 1 was being multiplied not by m, but it was multiplied by n. So I think that's the piece that's missing in your representation.
So I think it should be C, B, and I.
oh, the other way around.
Yeah.
Let me let's just think what this would be. So this would be so my one index, so I have A times B times I0, which is 0, plus B times I1, and then in my click, my I1 becomes 1, right? My first click, plus, and I'm just saying my whatever your I3 is. So if I3 corresponds to the C, which all cancels, and so I3 runs up, its range runs up to 99 or 100. So let's say we're at the first element here, and the next click, it would mean I1 is 1, and the first element would be I3 as 0. So I am getting B, and B is 2. Okay, now I think I see now the issue. Yeah.
You need the biggest.
Yeah, the other way. Yeah. Okay. Yeah. Actually, the size. Yeah.
So I think it's probably CB. It's definitely CB times something, but I don't know if the next one should be C or just B.
Okay, so you need to. Yeah, that doesn't work as nice. So you need to reshape this thing so that your smallest index is in the bottom, or like you say, this should, depending on the size of the factor, your biggest factor you maybe want on the left. Okay. So
I think it's CB, B, and nothing else.
Like CB, I0 plus B.
I think it's C, yeah. Yeah, because C.
Oh, okay. Plus, then just the, sorry, okay. I agree with you. I think that wasn't correct. Okay,
Great, thanks a lot for that, Carlyle. And so if I now have a family of objects running from I running from 1 to R, I could define their product to be a family of projection maps from a fixed object that's called the product, again indexed by the same I. And the condition, the property that defines it is that if I have any other object, let's say K as before, and I have a family of maps to each of these AIs called FIs, then there exists a unique arrow here making each of these triangles commutative. And what we're discussing here is a formula for how to define this when we're in the category of natural numbers. And according to what we discussed, this unique H that must exist will be defined as follows. H of X will equal, now let's transform that formula into this one. So the corresponding coordinates are given by the FIs, right?
Are you trying to adapt to this version of the 3 4 now?
Yeah. So it will be the sum to the sigma
Of the product.
of products.
Yeah.
It's a sum of products, right? And then each term in the product is a product of. Will we be able to write it in this way? It will not be, I don't think it will be possible to write it this way.
If we index our factors, you just say like A0, A1, A2, we can index our factors like that. Wouldn't that? And then we have like.
Yeah, but let's not change the notation at the moment. Let's go through the trouble of that notation. So the first term there is going to be the product of all the AIs up to up to the first without the first one, right? So I starts from 2 to R. And that was multiplied by that whole thing. Maybe I should write this in front. So that was multiplied by the f of 1 x. Then we have plus f2 of x times the product of, starting now from 3 to R. Is this correct? I'm following the pattern, but I'm not sure.
I think it's.
Yeah, I think so.
I think it at least follows a pattern.
And then at the end we'll have f R of x on its own.
Yeah.
So I would agree now with Chad that he said that
This is a proof that numbers suck.
when he said that we should not do this. What you meant was that we should not. You didn't mean that numbers suck. You meant that we shouldn't do this. And I agree with you. We shouldn't do this. Why shouldn't we do this? Because we have set theory. If we didn't have set theory, we would have to do this. But if at some point we want to actually do everything on the computer, then we will set theory again. And then we do this. Because introducing, embedding set theoretic constructions in the computer would be time consuming. It would be much more efficient to provide these formulas for the, am I right?
Yeah.
For
No,
the
what's
case.
nice about this is
Yeah.
that this would be, that tree would be how it's stored in memory, right?
Yeah.
Your matrix
Yeah.
or your whatever. And so the entries, you have to be smart in what your last index is, because that will be the entry, the most rapidly changing index, and then how efficient your algorithm or computation is, like how the thing is shaped.
Yeah.
Is this product that we defined in general associatively?
Up to isomorphism, that's something we still are going to prove. Okay, so let's go back to, we had a little diversion here, an interesting one. Let's go back here. We kind of came up with this idea of product, but now let's write down the formal definition for a general category.
So one thing that I was still wondering though, if we're defining H as, so the way that you wrote that H is as a pair fx gx, which didn't work with the natural numbers. But I am wondering, let's say your category has objects of a nature Z. How can a pair of two of those objects with the nature Z ever be of the nature Z?
I don't know what you mean.
So there
matrix set.
There you said H is equal to a pair of fx gx, right?
Yeah.
So in this case, if we were in a so I suppose say we were dealing with matrices, right? How can a pair of so there your F would map to would be mapping to matrices and G would be mapping to matrices. How can a pair of matrices be a matrix?
You can stack them this way or that way, right?
Okay.
But if it's matrices, in the category of matrices, that will not be quite a little bit. It will actually be, but I don't want to reveal the secrets there. So
Because I know that you can then take those pairs and then map it to a matrix, but a pair of matrices, is that not necessarily?
So we will come back to the category of matrices and see what they are there. Okay.
That's probably meaning like in a general case, but yeah, I suppose we're getting there.
So product of two objects in a category is a diagram of this kind, such that for any other diagram of similar kind, for any, I'm now stating this slightly differently because we learned that it's useful to think of this pair F and G as another diagram of the same kind. For any other diagram of the same kind, given by F and G. And it doesn't, when I say other here, it doesn't have to be a different one. The definition also applies in the case when F and G are pi1 and pi2. So for any diagram of this kind, there exists unique H going from K to n cross M, such that I1 composed with K, with H equals F, and I2 composed with H equals G. And we can draw a little illustration here that we had before as well. N, M, N cross M. And we've got here I1, I2, K, F and G, and this dashed arrow indicating the existence and uniqueness of H, making the triangles commutative. So we've been able to, okay, well, first of all, you can imagine easily that the proof we had that sum of two objects is unique after isomorphism by the reversal of arrows will transfer here. Everything is kind of symmetric. And so then we can claim that we've actually been able to capture addition, multiplication abstractly in any category. And in this experience, we noticed something remarkable, that one of them is obtained by reversing arrows in the definition of the other. So this process of reversing arrows emerges here, which is a curious phenomenon. And in fact, we can turn it into an ingredient of the theory, and it be a very powerful ingredient of the theory. If you have any category, you can always reverse arrows. You get a different category because the arrows are reversed. In a category, direction of arrow matters. But that category will very similarly behave in a reverse way. It is a kind of the notion of antimatter in physics. So any category has a reflection in the mirror, a ghost, called the dual category. And so multiplication in one is equivalent to addition in the dual. So these two notions lead us to the notion of duality in category theory. So that's one remark I want to make. Now, the other remark, which is something we will still elaborate on in the future. The other remark I want to make is that it will turn out that, well, first of all, let me say something general, that you take any kind of mathematical structure. It can be a group, it can be a ring, it can be a topological space, it can be a vector space, it can be a Hilbert space, anything that mathematicians study. In many cases, there are useful categories they form by usual structure-preserving maps that they consider in the study of those structures. Like for vector spaces, it will be linear maps, and for groups, it will be group homomorphisms and so on. And it turns out that the notion of sum and product of objects recovers the standard constructions in these fields. For groups, this will be direct product and a direct sum of two groups. Same for vector spaces and so on and so forth. So what is fascinating here is that abstracting an ordinary additional multiplication of numbers, very primitive thing, we are able to recover very complex constructions throughout mathematics of adding mathematical structures and multiplying them. But there will be some surprises as well. And the first surprise will be offered by the category of matrices. And those of you who want to get some kind of mark and credits for the course, which is an option, that's your homework, to calculate what is, so that make it a bit more clear, because there will be some students, I think, who are doing this course for getting acknowledgement at the end that they've done with the mark assigned to it. So the homework is describe sums and products in the category of matrices. And this is the category we considered in the first lecture. So a remarkable surprise awaits you there, which we will discuss next lecture. So the deadline for this homework is next Saturday, because we are going to solve this problem next Saturday. And after that, after solving this problem, we will formalize two notions. That will be the notion of isomorphism and the notion of dual category. And those who want to get 90% for the course can try to do the second homework as well, which is to formalize the notions of isomorphism that we touched on today, and what we briefly alluded to as dual category.
If we decide to do this, should we collect all of the homework sort of in a special place, or is it just going to get reviewed, the next week?
Yeah, so you need to send it to me by email. The homework should be sent to me by email. And you can do, if you want to, you can do this in a group work, and then you just list the collaborators. And next lecture, before next lecture, I'm going to send you a link where I will ask you please to register for it. Registration is free, but it's a way for us to have a proof that I wasn't talking here alone. It will be very useful for me if you register for the course. But because we are still beginning, we're still seeing who will attend, who will not attend. I haven't sent out the registration details yet. That I'll do it for the next lecture. Okay. Any questions before we finish off? Yes.
Can we go back to the formula? There's another mistake.
Is it another mistake in the formula? Okay.
It was the correct element.
Maybe that should be a third homework to fix the formula.
I think this will finally be.
I think my issue.
Mathematicians lost nerds.
When I worked with this, there was an implicit bordering. This I think should just be -1. Because if this is R, then you have each one of these can at maximum be the size of the whole tree. So then you have greater than n.
But then we're missing 2 terms because we started with 2.
Yes, so each one of these blocks should have R-1 terms because they represent this. And then when we add them all together.
They do have R-1 blocks because we started counting from 2.
But we have this one added as well. So this index can go up to. So if this was where's the eraser? Right, this F1 can go up to.
It can go up to FR. And when it's FR,
No, but I mean this F1 can go up to A1, right? Can go up to A1. But this is
we forgot -1, by the way. Yeah, we forgot subtracting 1.
Depends where we start counting.
No, but if
Yeah.
I didn't say that
this
we
yeah. But even so, right.
And then it can go up to A-1 because it will be F1 of X -1. So the correct form is you're right. There was a mistake on this because we should have written here. We should have been subtracting 1 each time. No, but how many? Now I'm lost because maybe it's not just 1 that's subtracted, but more than 1.
So all I'm saying is right. If this can go up to A1, then you can move that inside, and we just have the product of all the AIs.
Yeah.
But then this entire product is already the whole tree. So then we have R copies of the tree, which is too much.
Right.
So we want this one to be only this size. So then when we have R copies, we get the tree.
Okay.
So I think this should be.
So I feel that we should be punished for not being able to get this formula right in the first 2 tries. So then I would like to add a third homework. Which is to
I think that it's unfair for anyone to assume that I can comprise a formula of simple multiplication and
Please say it again. Sorry. Can you say it again?
I said I don't think it's fair. I don't think it's fair for anyone to assume I can compose a formula that comprises of simple addition and multiplication. That's not fair.
So you're not going to do this homework.
It depends. It depends how much work I have this week and how much work I have that.
Fix the formula we kept getting wrong. Yeah.
I was working my mind that the thing was already going to be reshaped, that if it's the factors of the number, then the first index is going to be the largest factor, and then
So very confusing. Actually.
So for full marks, it's sufficient to do 2 of the 3 homeworks. You don't have to do all 3.
In the first one for describe, and how should we, prove that the construction we give is
Describe what are they? Give.
or just describe, just describe them, or
So we describe what they are in the category of natural numbers.
yeah.
And now we want to describe them in the category of matrices. We got 2 natural. You remember objects? There are 2 natural numbers.
Yeah.
2 natural numbers. There will be something in the middle. You have to figure out what, and then you have to figure out the arrows, the matrices. You have to figure out which matrices are these, and then maybe you come up with the same formula as before for those unique arrows.
And can we we run into a similar problem that we do with the natural numbers, that we don't have the ability us to creating that formula. Can we extend the category, add more objects, or
So it will turn out that there things will be a bit easier. That's one of the things. But actually, I think even though it kind of we kind of ignored it both consciously and subconsciously. This is an interesting question, and fixing this formula would give us a description of products in the category of natural numbers, not just of two objects, but of any sequence of objects. So that's an interesting problem to solve, I think. But there, it might be a bit easier. We might not be forced to have such a complicated thing.